Okay, thank you. So my name is Maria Almeida, and I work at the Center of Microtechnologies of the Chemnitz University of Technology. And today I will talk about the crystallization of cobalt iron boron with laser for TMR applications. As a motivation, we have been working with laser annealing for quite some time now. A lot of focus has been given to setting exchange bias locally, which was proven to be very useful for accomplishing more linear sensors. In the case of GMR sensors, we have published these results where we can set exchange bias in opposite directions to sensors near each other, or even with an orthogonal kind of arrangement to have a two-dimensional sensitivity. So the next logical step is, of course, to see how this method can be used in TMR devices. In the particular case of cobalt iron boron MgO TMR layer stacks, we have an additional constraint. So here the annealing is not only for setting an exchange bias, but we also require this for crystallizing the cobalt iron boron layer. Cobalt iron boron is amorphous on deposition, and this is essential so that we have a growth of an MgO barrier with a good over 1 FCC crystalline structure. And so this annealing step will then, using MgO crystalline as a template for the crystallization of the cobalt iron boron, so that we have the coherent tunneling that gives rises to large TMR yields. And so, of course, this is known and has been studied in a lot of groups, but now we want to show that we can also use this laser method for crystallizing these layers locally. And this is what
sorry, Maria. We cannot see your slides. I don't know if you're changing them on your side, but at the moment we're still fixed at the first one.
Okay. And right now, like in this view, maybe?
Yeah, now you're on the second slide, yes.
Okay, so this was the motivation. I will try then to be fast. So we have been using this method for setting exchange bias. And we were able, as we see in these magneto-optical microscopy images, to set exchange bias opposite to each other on neighboring devices. And having them then aligned orthogonally, we have even shown that we can have two-dimensional sensitive sensors. And so now the next step is to use the laser method to crystallize the cobalt iron boron, as I discussed, to induce this the crystallinity that is required to have coherent tunneling in cobalt iron boron MgO magnetic tunnel junctions. And so we designed some experiments with simple layers for XRD measurements, in this case with cobalt iron boron layers with a capping tantalum layer or a capping MgO layer, so that we can also investigate different orientations of the crystallization. We investigated 2 different cobalt iron compositions and also had some samples annealed in furnace, so that we can investigate how a typical annealing with the temperature series and the time series can compare to this laser annealing method. And for laser annealing, we tested continuous irradiation at different scanning speeds and various laser intensities. And in our XRD measurements, we observed that the typical annealing in furnace led to on the samples kept with tantalum to the formation of a BCC cobalt iron phase with a good 110 texture, and we achieved coherence lengths vertical coherence lengths of around about 7 nanometers above 550 degrees. And with laser, we could achieve levels of crystallization which are comparable of around about 6 nanometers coherence lengths, which are quite comparable to those of 400 to 500 degrees Celsius. And now, of course, in terms of the applications, this is actually quite good, even if with oven we can achieve higher levels of crystallization, because if we also think about the typical timescales that are involved in here, with furnace, we were using 30 minutes annealing at least. And with this method, we are able to crystallize our layers with a typical dwell time on below the millisecond range. And of course, we can even think of decreasing the time going for post-radiation. But continuing our study, it was then necessary to also understand how the lattice, or if there were some changes to the lattice between the two methods. Because on one hand, we have the furnace annealing, which is, we have a very constant temperature and uniform, and with the laser is exactly the opposite. So we have large temperature gradients, and it's a very dynamic process. And what we realized is that the distance between the lattice planes measured with the XRD were actually evolving very differently with temperature or with laser intensity. So in the case of the furnace annealing, we see that we have decrease in the distance between the planes, between the out-of-plane planes. And when we measured the in-plane, when we performed in-plane XRD measurements, we realized that the measured planes were actually kind of expanded, which we believe is to do with the interface with the exact HCP ruthenium. And the annealing, the furnace annealing, actually works as, or helps the lattice compensate this expansion in plane. So we have a reduction out of plane to compensate this. But in the case of the laser annealing, we actually have an expansion in both directions. So in this, again, is most likely due to this large temperature gradients and to the dynamic of the process that we need to then watch out when we actually anneal real devices. Then we also, of course, measured samples kept with MGO, coming a bit closer to our applications where we want MGO to act as a template for the crystallization of the cobalt iron, in this case with a 100 texture. And we actually observed this in our XRD plots. The problem here is that due to our silicon substrate, we could not depict all the peak for all the temperatures. So we used kind of a trick, and we performed the measurements tilting the samples by 45 degrees. And by doing so, these off-specular measurements allowed to actually investigate more systematically our samples, and showing that we have a kind of evolution of the coherence length, which is similar to that of the samples kept with only tantalum. And we could, again, find a range of comparable crystallization levels with laser and with furnace. What we also noticed is that in the case of the crystallization with laser, the fact that the MGO has different thermal properties, so it hinders a bit the thermal conduction. And because of that, we have kind of a shift of the onset of crystallization, but also the onset of alloying or diffusion for lower laser intensities. And this is, again, thinking forward in how we want to apply this in our devices, this is also a crucial aspect that we need to take into account once we have other passivation layers. And finally, and this is where maybe this view is not optimal, but I will then shift a bit. So looking at the squid measurements we have performed on these layers, we see on the oven annealed or furnace annealed samples, we see a difference between the samples kept with tantalum or with MgO. And in fact, the samples, in the case of the samples kept with tantalum, we have a larger increase in coercivity due to the, as a function of the annealing temperature, which we believe that may be due to some lattice distortions at the interface of ruthenium with cobalt iron that may be hindering the domain wall motion through defects. And this is also what we actually, or at least it is very consistent with the change in the lattice plane, in the distance between the lattice planes that we observe from the XRD measurements. In the case of the crystallization with laser, we see that for the highest laser intensities, we see a dramatic change. Actually, we have a relatively, or we don't have that much increase, but at some point, I think the coercivity increases very significantly, and this would be again in line with the fact that due to the dynamics of the laser annealing, that we are more prone to have distortions on the lattice that may lead to this increase in coercivity. And so as an overview of this talk, we were able to show for the first time crystallization of cobalt iron boron with laser. And we were able to determine a window of parameters where we can achieve comparable levels of crystallization with laser and with oven annealing. And yes, we also have shown that there are some, the dynamic of the process, the gradients introduced by the laser also introduce some limitations, or may introduce some limitations on the process. And of course, the future scope of this work is now to prove that we can actually anneal devices successfully and achieve high TMR ratios. And this may open doors for not only standard TMR devices, but also for the integration of TMR devices with technologies where temperature may be an issue, technologies or substrates, for example. And finally, I would like to thank, of course, the team that contributed for this work, and also the contribution from other colleagues with samples or with help at BESI measurements at KMC2, and finally the financial support from the DFG, from the HCB, and from the Saxony state. Thank you, and
thank you so much.
You can ask me any questions now.
Thank you so much. So we have like 1 minute for a question. I see that Luis has a question, so
yes,
please.
Maria, thank you for your presentation. I would like to know, is this a pulse laser switching, or is a spot that is continuously switch? Is continuously sample?
I'm sorry, I cannot hear you very well.
Is this a pulse laser switching? Sorry, pulse laser heating?
This was continuous.
Continuous, okay.
But we are planning to also investigate pulse laser. Yes.
Okay, and how do you control the area of the heating? Which size are you heating?
Yeah, in this case, because for the XRD measurements we needed quite a large area, we opted for samples with 6 by 6 millimeters. But our laser spot is has 20 micrometers diameter.
Okay,
So when we go for devices, of course, we don't need to scan the sample like we are doing now for this specific XRD measurements.
Thank you for the questions and for the nice answers. If there is any more question, please use GatherTown or change emails or something. Now I think that we still have a problem with Mr. Brahim, so we're gonna continue with Francisco Gonçalves and his presentation. So you can start sharing your screen, unmute yourself, turn on the camera.
It's coming.
Dancing.
I take you guys can hear me.
Yes.
And I'm gonna hit play, and you're.
We are seeing the presenter view, so you should switch.
Okay.
Maybe at the top somewhere. Yeah, it's next to the X at the top right.
Top right.
Is the one with the that. Oh.
Ah, here. Thanks for your help.
Yes.
That works better now. Yes. Okay.
Yes,
very good.
Please.
Then good afternoon, everyone. So my name is Francisco. I will be talking about some recent studies on the agility of spin-all nano-oscillators. This is a team effort, and these are the team members. Just happens to be, I'm lucky enough to be presenting this to you today. So I will first explain a little bit what spin-all nano-oscillators are, and then I will move on to some experimental configurations and some experimental results. So what is a spin-all nano-oscillator? So it's essentially a bilayer structure that relies on a spin-all effect and spin-orbit torque effect to generate steady-state magnetization precession that occurs in the microwave frequency range. So this bilayer system comprises or consists of a non-ferromagnetic metal, it could be platinum, for instance, and it is placed adjacent to a ferromagnetic layer. So it could be permalloy, it could be anything you'd like. So what happens here is that a charge current with a certain density, it is heavy metal, induces accumulation of polarized spins in this case, top and bottom interfaces, and it's highlighted here by AtC-AtG, spin-all effect. And this pure spin current accumulates at the top interface and then transfers to the ferromagnetic layer up here in the form of a damping-like torque. And this process is then called spin-orbit torque. So upon correct choice of current polarity, current direction, and external magnetic field, what happens is that this damping-like torque can counter the Gilbert damping. So this SOT-like field-like torque counters the Gilbert damping. And then what we have is that the thermally driven spin waves or spin excitations give rise to sustained magnetization oscillations. So one of the requirements here is that we need large current densities so that this countering of the Gilbert damping is sufficient. And this is normally achieved in planar nanostructures. So I would like to, okay. So one can simply think of this as basically, so DC to RF converters. So we apply a DC current and we get an RF output. So these devices could be interesting and useful for instance, to drive spin waves into magnon conduits, for instance, or to act as RF emitters. There are also interesting subjects for synchronization in chains of magnetic oscillators. So, if I move on, so then this sets the stage for for our motivation, which is basically, so we want to learn how auto oscillation signals evolve in the time domain when driven by pulse stimuli. So basically, I am referring to applying voltage pulses in order to drive auto oscillations in this nanoconstriction region here. So this talk will then have two parts. One where I will just simply apply voltage pulses and see what the response of the SAG node looks like. And in the second part, I will apply both voltage pulses and microwave pulses in order to control the magnetization auto oscillation properties using an external RF source. So this here on the right is then the SAG geometry that we used. It essentially consists of two sort of disc-shaped nano-constriction, and the action zone is pretty much at the center here where the current densities are high enough. So it's important to note that the presumed current direction is along this plane, and also the external magnetic field is tilted in the direction orthogonal. I'm sorry, something is about to happen here. Can you guys hear me? Hello?
Yes, you're still
okay.
audible. Please continue.
Right. Okay. So then the technique we utilized to measure the auto oscillations is called time-resolved brilliant light scattering microscopy. So the acronym here is TR micro BLS, and it basically the BLS signal is proportional to the intensity of the oscillations at the measurement position. And using this method, we can achieve a sub-micron spatial resolution with nanosecond temporal resolution. So on the left part here, I am showing you the simple experimental schematic. We used an arbitrary waveform generated to create the voltage pulses, and the same trigger that we use for the AWG, we also use for the BLS detection. This is a very simple scheme. So before diving into the time resolved data, let us look at the time integrated BLS signal as a function of the pulse amplitude. And this probably for some people who are familiarized with the subject. So this is a typical representation for BLS spectra as function of applied voltage or applied current. So we observe essentially two modes. So the fundamental mode down here, and then the second harmonic mode up there. So that'll be at twice the frequency. So this main mode exhibits a downshift with increasing amplitude, and this is very much the main point here, and it will be important to keep this in mind for the next stages. So we also detect the second harmonic, which is obtained due to the fact that we are handling with a planar geometry. And for that reason, one can detect the second harmonic mode. So moving on now to a little bit of the time resolved data. So what I'm showing you here on this plot is frequency integrated BLS signal as function of time. So the different line profiles correspond to different applied voltages. Yes. So in addition to that, I will then include on the top part here the shape of the time profile of the pulse that I apply. We can identify the onset position and the onset segment here on the left and the outset segment here on the right. And obviously, this part is very different from that part there. And what I would like to point out here is that after fitting each one of these data sets with sigmoid curves where we could look at interesting parameters such as the amplitude, the growth rate, and the midpoint, we understood that for increasing voltages, we then see an increase in the rate on the growth rate of this auto oscillation profile, and which basically means that as we increase the driving power, then this rate goes up. In a way, it becomes more agile and has a faster response. So at the same time, we see that for large enough voltages, we always reach a kind of a steady amplitude state up here. So these are all characteristic behavior of the nonlinear response in spin-on nano-oscillators. So in addition to this, you may find that there are some little bumps in the amplitude. So for example, it's highlighted here by T1, T2, T3, and T4. So it perhaps is more constructive if we now look at the actual, or the raw time domain data that we obtained using this technique. So it's represented here. So now we have the BLS frequency as function of time, and the contrast is the count rate, the counts in the technique, in this technique. So we can see that for 100 nanosecond pulses, which is the same as what I've shown you before. So for this particular data set, I applied a voltage pulse of 1.4 volts, which is corresponding to one of the maximum values we got here. We see that, so at the early stages, so the onset segment and outset segments, we see this change in the frequency, which it's consistent with the fact that at the onset positions, we see a sharp rise in the voltage, in the instantaneous voltage, which means that we pretty much go from a low voltage value to a high voltage value, which means that the frequency shifts very quickly. And this is what happens here and here. So we then look at this frequency changes along in the intermediate segments of the pulse, which we attribute to the ringing effect of the circuit. And if we go to shorter pulses, for instance, 50 nanoseconds, 20 nanoseconds, 10, 8, and 6, what we observe is that then the BLS response simply gets truncated. We still see this decrease in the frequency at the onset and outset segments, and everything else just gets truncated, as simple as that. What is important to note here is that for the shortest pulses, with just a few nanoseconds, so we still observe auto-oscillations. However, it needs to be said that these are not very well defined in frequency. There is a certain frequency spread, if you see here, and mostly here and here. And this is because, in reality, what we are applying is basically an onset ramp and an outset ramp. So that explains the sort of frequency spreading. In addition to that, we observe a 50% decrease in the integrated amplitude, which is very much associated with that. So with that, I will quickly jump into the part 2 of my talk. So in this second part, I applied, in addition to the voltage pulse, I had an RF pulse. Okay, so if you look at this a small plot on the left, so I had a RF pulse on, and then eventually I turned on my voltage pulse. Okay, it needs to be said that the frequency of the RF pulse was at twice the auto-oscillation mode, and this is how I achieved an efficient pulse injection locking signal. So before going to the time resolved data, I would like you to see a typical frequency, so measured frequency on the vertical axis against the applied external RF frequency on the horizontal axis. And what we see is that for low enough external frequencies, the auto-oscillation mode remains constant in frequency, but the moment we reach the injection locking region, then the auto-oscillation mode drops in frequency, and then it has a linear behavior with increasing external RF frequencies, but then it drops again. So this is typically identified as an injection locking range, which we just show that works also in pulsed modes, in pulsed operation. And it is also relevant to then look at the time profile of the BLS signal. So before we reach the injection locking range, we see a slow increase rate at the onset, and we see some oscillations in the amplitude of the BLS signal. The moment the injection locking range is reached, we then see quite a rapid increase in the growth rate at the onset segments, and so a sort of a more so a flatter steady state response. And this is again, so I think one of the interesting findings here, so injection locking increases the onset rate of the auto oscillations. And so having these two important experiments, so putting them together, so I will try to now demonstrate how the combination of voltage pulses and external RF pulses can lead to interesting temporal patterns or amplitude patterns. So here on the left, I am showing you a voltage pulse with 3 RF pulses, so with a train of 3 RF pulses. And what we end up with in terms of auto oscillation response is something that resembles a pattern with an amplitude modulation at constant frequency. As we can see that here, there's a maximum, a minimum, maximum, minimum, and so on. So in another example, so in another scenario, we may apply, so something that I describe on the right, we may apply a train of voltage pulses here which here alternate between 1 and 0.5 in amplitude. So we can actually obtain amplitude modulation at 2 different frequencies. So highlighted here, and then the other frequency down here. And of course, this can be interesting for a range of applications. So these results here illustrate how powerful time domain patterns can be.
I'm sorry, Francisco, yeah. I must cut you because we are in a tight schedule.
Okay, so then I will just move on to the concluding slide.
Yeah,
and
if
I
you
am
just
ready
conclude quickly, and then the discussion can be on Gathertown.
Very good. Thank you for understanding. So in conclusion, so the growth rate of this nonlinear effect that leads to auto oscillations depends on amplitude of the driving input signals shown on the first set of experiments. The second one shows a very similar response, but in this case using injection locking. And with this, I would like to conclude my talk, and please follow up on the recommended reading regarding applications for this topic. Thank you very much.
We definitely will. Thank you so much for the interesting presentation, Francisco. And I would say that now we try to go for the next talk, that is Franz HERLING. Please, Franz, you can try to unmute yourself, share the camera, and get ready with the presentation. And then, as usual, at 10 minutes, I'm going to give you a mark.
You should be able to hear me and see my slides now?
Yes, we can hear you and see your slide. You can start whenever you want.
That's great. Thank you very much for the conference and for this worldwide science event. Very grateful that we can share our recent results. And I want to also say thank you to the European Union, who is funding my PhD via the QuestTech program. And of course, to all my colleagues that worked on the results that I'm presenting today. In our group, we are using 2D materials for spintronic application. And as always in magnetic conferences, it's kind of one of the only 2D material talks. So I will quickly explain why 2D materials are interesting for spintronic applications. The best known is probably graphene, that has a long spin diffusion length and is a prototypical material for spin transport. But there are other members in the 2D material family as well. For example, transition metal D chalcogenides that have a strong spin orbit coupling, that have valley polarization, and have been used for the optical generation of spin currents. And the advantage of 2D materials is that we can combine them in van der Waals heterostructures, and we can combine the properties via the proximity effect, and we can add functionality for spintronics. For example, the spin to charge conversion directly in graphene, or the magnetic field free spin precession. And with that, I want to start. For materials with spin orbit coupling, you will have spin precession due to spin orbit fields. So the electron essentially sees an effective magnetic field around it will precess with a period tau. Tau is O here. And if we want to have coherent spin precession, we have to achieve the strong spin orbit coupling regime so that this period is roughly in the same time frame as the tau that is stopping the precession. Normally, this is a scattering event, for example. And in our proximitized graphene, so graphene with a TMDC on top, we have essentially 2 spin orbit coupling mechanisms. The first one is the Rashba spin orbit coupling. Its origin is the inversion symmetry breaking at the interface of the 2 flakes, and it will be perpendicular to the potential difference here along Z, and it is perpendicular to the momentum. I think most of you know this picture of the Rashba spin texture in the energy dispersion. So following that, the Rashba spin orbit field will be parallel to Y, so it will make the spin that is pointing along Z precess. That means it's governing the spin relaxation time for out-of-plane spin. So if we want to achieve this strong spin orbit coupling in the out-of-plane spins, we have to increase the momentum scattering time. Unfortunately, these ballistic regimes are normally, especially in semiconductors, limited to low temperatures. So that makes it quite unfeasible for device application. However, the second spin orbit coupling that we have in proximitized graphene is the Valley-Siemens spin orbit coupling from the TMDC. Its origin is the broken sublattice symmetry due to the stoichiometry of the TMDC. It has an opposite sign for the K and K prime valley, and it's parallel to Z. So it will make the spin that is in plane precess. And the characteristic time scale here is not the momentum scattering time anymore, but the intervalley scattering time, as the effective magnetic field will change for K and K prime valley. And as I told you, in TMDCs, there is a strong valley polarization that is imprinted into the graphene, as well as the strong spin-orbit coupling. So in that case, we can achieve the strong spin-orbit coupling for room temperature in a diffusive system. How can we measure that? We are using the normal lateral spin valve that is used in a lot of spintronic research, where we have a graphene channel with two ferromagnetic electrodes to inject and detect spin, and the TMDC in the middle. And if we now sweep the magnetic field along Y to change the magnetization direction of our electrodes and measure the non-local resistance, we pick up this very standard lateral spin valve signal. But what we see is that we have a reversed sign. So normally we would expect that the anti-parallel state has a lower resistance than the parallel state. And the reason for this is the first signature of the coherent spin precession in the strong spin-orbit coupling regime. So while the spin is injected and travels through the channel, it will precess by 180 degrees under the TMD and will be picked up essentially as an anti-parallel signal. If we now measure the Heimlich precession, where we sweep the magnetic field along X, we see for this anisotropic Heimlich curve that has been theoretically predicted and already experimentally observed in different graphene TMDC heterostructures. So we see the split that we already saw in the lateral spin valve for zero field. And then if we increase the field, the spin will precess out of plane. And as the out of plane spin lifetime is governed by the Rashba spin-orbit field and is longer than the in-plane one, we will have these enhanced shoulders for both magnetization directions. And then if we increase the field even more, what happens is that we pull, the magnetization of the electrodes into the direction of the field. So we will measure the same signal for both initial magnetization directions, and we will measure this lower anti-parallel resistance value due to the spin precession under the TMD. So this Heimlich curves and this characterization of the spin transport shows us very clearly that we achieved the strong spin-orbit coupling regime and that we have coherent spin precession. And what we did next is we added in our device an additional DC current with which we control the diffusion in our channel. This is an experimental method that has already been used in graphene. And what we can see, if we look again at the lateral spin valve signal, that it is 0 for no applied current, and that it changes sign if we apply a positive or a negative current. And to explain that, we have to look a little bit closer into the two different valleys that I mentioned. So we have this K and K prime valley in this graphene TMDC heterostructure. And as I told you, the Valley-Seemann spin-orbit coupling field will point in different directions in those two fields. So while the spins start injected parallel, they will, while they go through the channel, precess in different directions. And when they reach the other side, they will essentially cancel each other out so that we measure no lateral spin valve signal. If we apply now negative current, we essentially accelerate the spins while they're diffusing through the channel. So they will have less time to precess. So we will measure essentially a positive normal lateral spin valve signal that is probably well known. And if we apply a positive DC current, what we essentially do is we decelerate, we slow down the spin. They have more time to precess while they travel through the channel. And they precess so much that we again measure this negative lateral spin valve signal here. So essentially with the DC current, we can tune the lateral spin valve signal. So if you look at here at the blue curve, we can see that we can tune from a positive sign to a negative sign with applying the DC current in the channel. And when we change the backgate voltage, what we see is that the value of the lateral spin valve signal also changes. And the reason for that is that the backgate voltage in bilayer graphene also changes the diffusivity. So essentially you can think about it as you, with the backgate voltage, also change this diffusion of the electron in the channel. So we essentially have another knob that we can play with controlling the speed with which the electron is diffusing and how much time it has to process. So if we keep the DC current constant, we can sweep also the backgate voltage, and we can control the sign of the spin signal going down to negative close to the Dirac point, where the diffusivity is the lowest. Here, the Dirac point is this blue line. And then when we go from hole to electron, we see that the sign is changing again as the effect of the current is changed because we're changing the carrier type in the channel. So this is a second knob that we can change the signal with. And both of these, so to say, knobs to change the spin signal in our device also work at room temperature. So here's one curve where we can change with the backgate voltage the signal and also with applying different currents. So what we've essentially done here is we've realized a data-dust transistor at room temperature due to the strong spin-orbit coupling that we can only achieve because we're using proximitized graphene as a heterostructure. And in this strong spin-orbit coupling regime, we can electrically control the coherent spin precession around these spin-orbit fields. And that is a result that we've just recently published in Physical Review Letters. And with that, I want to come to a somehow quicker second part, where I want to talk about the spin-to-charge conversion. The device we're using is essentially a Hall bar with proximitized graphene that we developed in our group and that recently other groups have adapted for their needs. And in this proximitized graphene heterostructure, there is the theoretical prediction of spin-to-charge conversion.
2 minutes.
And I'm just going to go here to this graph where we see that due to the spin Hall effect that only converts out of plane pointing spin, we can measure this non-local resistance. And then if we sweep the magnetic field, we see this anti-symmetric Handler curve, which is a clear sign that we have spin Hall effect and spin to charge conversion due to spin Hall effect. And if we take the difference between those two curves, we can extract the spin to charge conversion parameters. And we see that at all temperatures, the figure of merit, so the spin Hall angle times the spin diffusion length, is at least an order of magnitude larger in proximitized graphene than in this prototypical spin Hall effect material platinum. And we can see that with a backgate voltage, we can tune the spin to charge conversion from turning it off to amplifying it, and the maximum value we can achieve in our system at 100K is 40 nanometers. So 2 orders of magnitude larger than platinum or other comparable spin to charge conversion systems like topological insulators. And this is the figure of merit also for Rashba Edelstein effect systems, whereas where the conversion efficiency is also given with the units of length. So as a quick summary, to come to my last slide, I showed you that we can use these materials for spintronic applications. I showed you the spin precession, magnetic field free due to the realization of the strong spin orbit coupling regime for the first time in a diffusive system at room temperature. And I also showed you the electrical control of spin to charge conversion, which will be important for integrating future spintronic devices into electronic infrastructure. And if you have any questions about these results, please feel free to write me an email or ask the question now. And as a final year PhD student, I also allow myself to say that if you have any interesting postdoc opportunities in the next year, I'm very much looking forward to hearing from you. And I'm also looking forward to get any comments or questions now or later in the chat. Thank you very much.
So thank you so much, Franz, for this interesting presentation. As usual, I encourage people to raise up their hands if they have any sort of questions. We still have like a few minutes for 1 or 2 questions. Okay, I guess there is no one. So I'm going to be the one asking a small question. I was really interested by that transistor that you showed, the main result of the first section. And I was wondering, how does it, like, did you actually fabricate it?
Yeah, so in this sense, this picture is more or less a sketch of the device itself. where we have a graphene channel with a TMD, in this case above, but for the picture we put it below. And these two electrodes are essentially our ferromagnetic electrodes that we use for the device. And we can control essentially, so to say, one transistor with a backgate voltage and this DC current. So we essentially realized one, but I think that's also always the first step, to realize one transistor, and then my professor always told me in physics is 1, 2, and then it's many. So only 2 more steps till application.
Yes, I definitely agree with this. Do you have any? Oh, wait, we have a question from the audience that maybe is more interesting than mine. So Jun-young, if you want, you can unmute yourself.
Hey, sorry, just a quick question. Yeah, thanks for the talk. So for the first part, you saw us the in-plane Hanne measurements for the I guess to tune the detector signal in your local device. Is it also possible to do the out-of-plane Hanne effect, or is it limited in the graph? Sorry, I'm a bit new to these systems, but I know in the semiconductor systems, I think you can typically do the out-of-plane Hanne to characterize the spin diffusing time and stuff. Yeah.
So theoretically, it's also possible to do out-of-plane precession, especially in the context of spin-to-charge conversion. This is an interesting topic, as you want to decide which spin-to-charge conversion mechanism you have. You want to measure spin precession out of plane or in plane to see if you're having an anti-symmetric Hanle curve, and then you can conclude if it's spin Hall effect or Edelstein effect. The problem in a lot of graphene devices that we also run into in our devices is that you have a strong magneto resistance if you're applying an out-of-plane field, which normally covers, even in the non-local geometries, your spin signals. If you've seen the scale, like we're measuring here of like single milliohms, the spin signal in our device, and the resistance of graphene, which is a high resistive material, is often in the kilo ohm range. So then
it's ordinary MI
magneto resistance covers for the out-of-plane spin precession often your signal. But theoretically, it should be possible. You have to really design your device to make it possible. And in this case, it was not necessary because we were interested anyway in the precession from in-plane to out-of-plane. So yeah.
Okay. Yeah. Thanks.
I'm sorry to cut you. Now we need to move on to the next talk. If you want to continue talking, well, now it's your turn, Jun-young, so it's difficult for you to keep on this conversation, but maybe after your talk, you can go in Gathertown and grab a beer and discuss about this more. So if you try to unmute yourself and share your slides to see if everything works. We cannot hear you right now. I think that you're muted.
Yeah, I think I'm muted. Yeah,
right.
Let me share my screen. Do you see my screen okay?
Yes, perfect. At your mark.
Okay, great. Okay, good day, everyone. Thank you, the organizers, for this opportunity to present our recent work on tuning spin-orbit talks across the phase transition in vanadium dioxide and nickel-ion heterostructure. So this was a joint work by the Johannes Gutenberg University Mainz, which I'm currently in, and also with the Jülich Forschungszentrum in Germany, and the UC San Diego for the vanadium dioxide films. Okay, so just an outline. So I will start the talk with the motivation of the projects, and then I'll briefly introduce the methodology, which is the spin torque FMR, in case the audience is not familiar with the technique. And then I will then move on to the growth and fabrication of the field to nickel-ion STMR devices. And then I will present the main results, which is the change of the Gilbert time parameter and the current-induced spin-orbit torque in this bilayer structure across the insulator metal transition. And then I will finish with a summary. Okay. So for the motivation, so the vanadium dioxide is an interesting material because it goes through this structural and the resistivity phase transition with a hysteretic resistivity change of up to 4 orders of magnitude at a temperature slightly above the room temperature, so somewhere around 330 to 350 Kelvin. And because of this large change in the resistivity, it has been actively studied for sort of phase-based electronic applications. For us, our interest as kindled by sort of observation of this large spinel angle that's comparable to that of platinum in a metallic vanadium, where it then sort of enabled that possible spin-orbit-torque devices with a large spinel angle or large spin-orbit-torque efficiency without using heavy metal elements. So there's some application potentials. So in this work, we investigated this vanadium dioxide and the nickel-ion bilayer for the any current-induced spin-orbit-torque effect using ST-FMR technique. Okay, so just a quick on the methodology. So the ST-FMR technique is a powerful and interesting technique for quantifying the current-induced spin-orbit-torques in a heavy metal ferromagnetic bilayer. So typically in this sort of the heavy metal and the ferromagnetic bilayer, where the main idea or the main experimental procedure is to introduce the RF current into the strip, and then this RF current in the heavy metal produces the oscillating oyster field into the ferromagnet. That, and when with an correct external field, it induces the ferromagnetic resonance of the ferromagnet, and then this oscillating FMR with the RF current produces a rectified AMR effect that we can measure by measuring the voltage across the strip here. So typical ST-FMR looks like this. As you sweep the field, we see a drop in the voltage across the strip as the signs of as a one way to measure the ferromagnetic resonance and the technique. What we do to quantify this current-induced spin-orbit-torque is to the so-called this modulation of damping technique, where we apply the additional DC current into the strip, and then this DC current, either by the bulk spinel effect in the heavy metal or the in either other interface effect, such as the interfactional spin galvanic effect, inverse spin galvanic effect, that creates this additional spin accumulation in the interface. And then this spin accumulation either narrows or broadens this width of the FMR peak we observe. So by studying the systematic sort of the DC dependence of the width of the peak, we can quantify the amount of torque given to the ferromagnet, and then from that we can estimate the effective damping-like spinel angle in the system. So in order to do this in the bilayer structure with the vanadium dioxide, we first deposited the 70 nanometers vanadium dioxide films by reactive sputtering. This was done in UC San Diego on the alcott sapphire. And then if you look at the XRD, you can see the polycrystalline growth of the VO2 films on the sapphire substrate. And then if you look at the AFM of the 70 VO2, we can see this island kind of growth with a surprisingly quite large 6 nanometer of the RMS roughness of the system of the surface, mainly because I think due to these pits and the island kind of structure. Regardless of this structure, we can observe still very prominent insulator to metal transition with about 3 to 4 orders of magnitude change in the resistance. And a narrow temperature range of around 10 to 20 Kelvin at around 340 to 350 Kelvin. And then on top of this film, we deposited 5 nanometer nickel ion and 2 nanometer MgO in mines by sputtering. And then when you characterize this nickel ion film, the saturation magnetism of these films are not too far from the bulk nickel ion value, which forms that there's a negligible magnetically dead layer formation between the interface of the VO2 and nickel ion. Okay, and then to fabricate these films into the structure for the ST-FMR measurements, we patterned this film into 10 micrometer wide strips using E-beam lithography and the argon ion milling. And then we use the Peltier element that's placed underneath the sample holder to control the sample temperature between either -10 degrees to somewhere around, I think, 80 or to 90 degrees Celsius. Then we can then measure the device resistance, so temperature dependence of the device resistance. And now we are measuring the resistance of this bilayer structure. So you can still see the transition as you go heat the sample to the saturating where the VO2 is become fully metallic to the when the VO2 is fully insulating. When it's fully insulating, we now see the resistance of the nickel ion layer, in this case somewhere around 170 ohms. And then and when the VO2 is fully metallic, we see the combined resistance, where we can estimate the current distribution between the VO2 and the nickel ion to be roughly 1:1 or to 60:40 at the fully metallic phase. Okay. Then this is the then we can do the field sweep with the fixed RF current to measure this ST spectra, which we measure like this. And then if we can then decompose this this data into the combination of the symmetric and the anti-symmetric components, Lorentzian components, to separate the effect from the Oersted field or the field and field-like torque to the effect of the damping-like torque. And then if you look at the frequency dependence of this width, we see usually a linear relationship with the frequency. And from the gradient of this line, we can estimate the effective Gilbert damping parameter, which we will discuss more in detail in the next slide. But as we then increase the temperature, so this is the room temperature. As we increase the temperature, we see a reduction of the amplitude of the STFMR signal. That's because now as the temperature increases, the VO2 becomes more metallic, and then more current goes to the VO2. And then this AMR signal is proportional to the current going to the nickel ion layer. So hence, this is the reduction of the signal as expected. Okay, then we first look at the temperature dependence of Gilbert damping parameter. So if you first look at there's a black line, so which is the device resistance, we see the device resistance decreases as we increase the temperature into in the metallic state of the VO2. But now we see the transition is wider than the unpatterned film, which we attribute to possible edge defects from the strip patterning. But more importantly, the alpha starts somewhere around 0.03 for that's quite close to the Pomeroy value, which then increases into around factor of 2 to somewhere around 0.06 as the VO2 becomes metallic. And then as we decrease the temperature again, it goes back to the room temperature value. Then we found this nonlinear variation of alpha with temperature to be the effect of this increased spin mixing conductance as the VO2 becomes metallic. So hence it's increased at the high temperature. Okay, then we look at the current induced spin-orbit torque by looking at the DC dependence of the STFMR spectra. So we applied additional DC current as shown here, and the ±1 milliamps. And then you can see there's a slight change of the width of this peak. You can see kind of from when we got to +1 milliamps to -1 milliamps. And when you look at this systematically, we can look at the sort of the linear relation of the width of the peak with the DC current. And then from the linear relationship, we can estimate the torque to be somewhere around, I think, 10 millitesla per milliamps, which was quite surprising because this was actually quite large even compared to the archetypical the heavy metal ferromagnet the bilayer systems. But what was more surprising is that when we increase temperature to the 355 Kelvin, so that the VO2 is fully metallic. Yeah. If you look at the given field directions, if you look at the black points here, the relationship is negative, but at the room temperature it is positive. So this the change and the sign reversal of the linear relationships suggests that the spin-orbit torque direction has changed. So if we performed a few more measurements at the intermediate temperatures, and indeed we see this reversal of the spin-orbit torque as we across this insulated metal transition. So this suggests that there are two competing mechanisms for the spin-orbit torque that's present in this system. And then we discussed this with our theorist colleagues in Jülich. and they calculated the spinor conductivity of a metallic VO2, and then obtained the value of somewhere around minus 100 Siemens per centimeter, which then matches the sign of the spin-off we observed at the high temperature phase, and then roughly matches the magnitude of our signal. And then as the competing mechanism, we suggest that it could be the self-induced torque, or this anomalous spin-orbit torque in this 3D the pomeroy that usually has a positive spinor conductivity. Hence, it competes with the bulk spinor effect of VO2. So we suggest that the competing effects of these two spinor torque generation could be the reason between this reversal and the modulation of spinor torque across the insulator metal transition. Okay, with that, I come to the summary. So we observed, we investigated current-induced spin-orbit torque in the VO2 nuclei via STFMR across the VO2 phase transition. We observed around factor of 2 increase of in alpha, which we attribute to the increased spin mixing conductance as we go across the insulator metal transition. And then this modulation of the sign reversal of the current-induced spin-orbit torque, which we see as a competition between the bulk spinor effect in metallic VO2. And the self-induced torque in the nickel ion. Okay, with that, I thank you for your attention and I look forward to the questions.
Thank you so much for this nice presentation. We have now a few minutes left for questions, so I invite anyone who has any questions to use the Zoom function to raise their hands. Okay, I guess not. So I just have a very quick question, just clarification. At what temperature were these experiments performed? And especially like how does the ambient temperature influence this sort of switching? Mm-hmm.
Thanks for the question. So we performed the measurements at a temperature range between the room temperature and then up to somewhere around 400 Kelvin, and the maximum temperature I think for spin-orbit torque was somewhere around 350 Kelvin, which it encompasses the VO2 phase transition as we observed as the device resistance. As you mentioned, the second part of the question, the ambient temperature will affect it because it is in an open environment. So I think at the high temperature, I think there will be a continuous heat loss to the atmosphere, which we have not fully characterized. But since the temperature is changed by the Peltier element right underneath the sample. So and then the temperature is measured by on top of the Peltier element next to the sample. So we expect the sample temperature to be very similar to what we measure. But there could be something as the STFMR measurement includes a fairly large current into the strip. So this temperature at the sample could be a bit different, as we actually observed. So in this intermediate temperature where the phase transition is changing quite rapidly, we saw a large change in the sort of device resistances even during the measurements. So this could be important in characterizing the exact state of the VO2 at that particular temperature. Yeah.
All right. Thank you for this clarifying answer. Sadly, we don't have time for any more questions, but I really invite you to go to Gathertown and ask more questions to Mr. Kim there. And now we could proceed to the next talk. That will actually be the one that we had a problem before from Mr. Brahim. So we have the pre-recorded talk that will be shared by the Procom member who said.
Yes, I said. Yes. My name is KEHILECHE Brahim. Yes. My name is KEHILECHE Brahim. Magnetic electro and machine mechanical caloric materials comparative study in refrigeration free materials, Mechano-Caloric materials. Introduction.
My name is KEHILECHE Brahim, University
Yes.
of Media, Algeria. Magneto, Electro, and Mechano-Caloric materials, comparative study of refrigeration systems. Introduction. The refrigeration sector, including the air conditioning and air cooling sector, faces several major challenges today. Solid-state refrigeration is a promising technology for the production of cold. The main element of the solid-state refrigeration is the active caloric regenerator, ACR, made of magneto-caloric, electrocaloric, elastocaloric, and barocaloric, electric field, magnetic field, and mechanical field. The operation of regenerator is complex. The operation of ACR, active caloric regenerator, is complex because it is characterized by transient and steady state operation and by microscale and macroscale models. The objective of this paper is to compare the energy efficiency of an active caloric regenerator based on magneto-caloric effect, electrocaloric effect, elastocaloric effect, and barocaloric effect using a 2D numerical model by COMSOL multiphysics in terms the temperature spin, COP, and cooling power. ICR system description. The active caloric regenerator ICR with the cold height exchanger and the hot height exchanger respectively, with ICR made in parallel plates. Comparison between magneto-caloric, electrocaloric, and mechanical-caloric ICR. The regenerator made in parallel plates, 54 plates, based on magneto-caloric, electrocaloric, and barocaloric elastocaloric materials, and 53 channel fluid. The velocity and the frequency F equal 2 Hz. Caloric features and thermodynamic of magneto-caloric material and electrocaloric material, elastocaloric material, and barocaloric material. The thermodynamic cycle for the active caloric regenerator, ICR, example, comparison between conventional refrigeration technology and electrocaloric refrigeration cycle, solid-state refrigeration. The difference in Gibbs free energy of caloric materials, the internal energy, entropy, magneto-caloric effect, electrocaloric effect, elastocaloric effect, and barocaloric effect. Elastocaloric effect and barocaloric effect, mechanico-caloric effect. and the caloric effect, Maxwell equations, entropy change for four materials, entropy change and temperature adiabatic change for electrocaloric, magnetocaloric, magnetocaloric, and elastocaloric, barocaloric effect. And Navier-Stokes and energy equation, two equation Navier-Stokes, and solid and fluid. Results and discussions. We have developed a 2D model of ICR with console multiphysics, which can support annealingcaloric materials, magnetocaloric, electrocaloric, elastocaloric, and barocaloric comparison between four materials made in parallel paths. Regenerator ICR. In the investigation introduced in this work, the active caloric regenerator has been tested with many materials. For example, gadolinium for magnetocaloric materials, electrocaloric, elastocaloric, and barocaloric, respectively. The 2D temperature distribution of the system during a cycle. In figure 3, we can observe the evolution of temperature. The best result obtained with magnetocaloric material, 277 Kelvin. The system is initially at a temperature of T0 the 2D temperature distribution for ICR 1, 2, 3, 4. Magnetocaloric effect T cold equal 277 Kelvin and electrocaloric materials T cold equal 278 Kelvin. The best result. Caloric effect as function of temperature. In figure 4, we can observe the evolution of caloric effect as function of temperature for the four types of ICR, magnetocaloric, electrocaloric, elastocaloric, and barocaloric materials. The best result was obtained by ICR based on magnetocaloric effect and electrocaloric materials. Electrocaloric, magnetocaloric, and electrocaloric. The evolution of the temperature gradient along the regenerator. Figure 5 shows the temporal evolution of the temperature gradient in the solid with the system operating at zero charge. In the initial state, the solid is an initial temperature of 298 Kelvin. During operating, the temperature gradient increases and it approaches a curved profile with a temperature difference which depends on the operating parameter. Figure 5 for magnetocaloric materials. The 2D velocity field, inlet, outlet, fluid. Figure, we can observe in figure the fluid velocity decreases from the maximum in the center of the microchannel to zero value of the boundary layer maximum. Figure 7. Cooling power and CoP as function of temperature. The best performance was in the ICR based on Magneto-Caloric effect and Magneto-Caloric materials and Electro-Caloric materials. CoP as function of time and cooling power as function of time. The maximum in Magneto-Caloric materials. Conclusion. The objective of this work is the design of I2D multiscale and multiphysics numerical model with capsule multiphysics intended to simulate the behavior of ICR refrigeration system using Magneto-Caloric, Electro-Caloric, and Elasto-Caloric and Barocaloric materials. This analysis of the functioning of the model and the sensitivity of the parameters help us to improve understanding to highlight to influencing parameters and to study the interaction between the parameters and their impact on the total performance of the system. It makes it possible to draw parametric behavior maps to help design future ICR refrigeration system at room temperature with better performance and lower cost. Thank you.
Okay, thank you so much for this talk. It was a bit complicated, but eventually we figured out how to make it happen. And due to the problems in your internet connection, I would suggest not to have any Q&A session right now, but rather to, if there is anyone who has any question to follow up with Brahim, please just send an email to him. I'm just sending in the chat the email. Otherwise, you can also find the same identical email on the booklet of the conference. And yes, so now we have a few more minutes before the next session, I would say, unless we want to start earlier, but I don't think so. So I just suggest that we just have like 5 minutes for a small discussions if we want. And then we start with the American session 7.